Okay, so for the video, this is a revision seminar for Maths 1B in 2013, and we'll be talking first about Rollies Theorem and the Intermediate Value Theorem and that sort of thing. Okay, so as you know, Mathematics 1B is probably not named correctly. It's more Mathematicians 1B. Doing maths is more about learning how mathematicians think than about learning maths per se. And one thing you'll be learned in Maths 1B is that mathematicians really like proofs. So you don't have to learn to like them, but you do have to learn to live with them. Because if you're going to continue to talk to mathematicians, that's what will happen. So they like to have really nice theoretical underpinnings for anything that they say. So when you're solving a problem, most of us are happy with something that's good enough. Mathematicians like it all to fit into this neat theoretical underpinning that everything works nicely and all the theorems are true, and mathematicians just love proofs. So I'm hoping that some people have some past exams on hand that have proofy questions that they're worried about, because I can work on them. But first I'm just going to go through somebody's notes, which I've just borrowed, and find the theorems. So so you've learned several theorems in calculus that concern derivatives. So calculus theorems about continuity and differentiability. A good approach, especially in a maths course, is to see if you can sort through your notes and sift out the bits that are really important. And one thing you can do is sift out the theorems and write all the theorems down, and sift out the definitions and write all the definitions down. And all your examples can go in their own place. And if you reorganise things like that, it can be a little easier to see what's going on. I particularly recommend this now, because in Engineering Maths 2A, you'll need to do that, because they'll be embedded in the general flow of the conversation about differential equations that's in Engineering Maths 2A, if you happen to do that. And also, if you ever do any more maths courses like multivariable calculus or real analysis, so you're going to have to do that too, because they'll just be embedded in everything. So working your way through and finding the names of the theorems and writing them down is a really good plan. So we've got three main theorems in calculus, I think. There is the Intermediate Value Theorem. And this doesn't talk about derivatives, it only talks about continuous functions. And the Intermediate Value Theorem says, let's see if I can remember it off the top of my head, if f of x is a continuous function on the interval a, b, then for any k between f of a and f of b, there is a c with f of c equals k. That's the Intermediate Value Theorem. And it's perfectly reasonable to write it mostly in words like that. And in fact, the Intermediate Value Theorem is quite difficult to write without using words, because we don't know which way around the FA and the FB are. So that's the exact statement of the Intermediate Value Theorem. It is not unknown in exams for them to just ask you what the theorem is. Okay? And so you will write precisely that. This isn't English, you don't use your own words, you use their words. Okay? So that's great and it's lovely and it has a statement like that. But what you would like is something to understand it And understanding means that you need pictures and stories and connections to other stuff. So the picture goes something like this. You've got your A and you've got your B. And your function, you know, goes through those points, but you're not sure where the function is yet because you haven't been told what the function is. And that would be f of A there. And that would be f of B there. And you know that no matter what the function is, as long as it's continuous and goes through those 2 points, it must pass through every y value in between. That's what it says. So let me just see if I can find something that will, because I didn't bring a piece of string with me. Looks like my microphone cord is the best one. I'll just have to rely on the lectern microphone for a second. You have a function that goes between here and here. It might be straight, it might be curved in any number of ways, but it doesn't matter what it's like, what shape it is. It might even do this, right? It doesn't matter what shape it is. No matter what shape it is, as long as it's continuous, it will pass through any horizontal line. Okay, this is my case, somewhere in between f of A and f of B. So no matter what shape it is, even if it's got kinks, it doesn't have to be differentiable. It can be any shape at all. It will pass through the horizontal line. That's what the intermediate value theorem says. Okay, it might pass through the horizontal line multiple times, but there will be at least one place where it has to cross that line. And the x's that give you those heights, they are called c. And there might be more than one. It could be any number of them, but the theorem only guarantees there to be one. That's what the intermediate value theorem says. Okay, so what does that mean? Well, it means that you can at least prove that something has a zero by showing that it's below zero somewhere and above zero somewhere. So just as an example, do I pick a really mundane example? I'm trying to think, well, it's really hard to think of complicated ones. I'm sorry, I can't think of one off the top of my head. Actually, just a second. Sorry, just give me a second. Really hoping that works. Just don't fill the numbers in yet, I might have to change them. So, show that that function has a 0 between -1 and 3. And you go, well, I'll just plug in -1 and I'll plug in 3 and I'll see what I get. Y of -1 is, which is 1 minus 2 minus 7, which is negative, right? And y of 3 is, that's 9 plus 6 minus 6, which is plus 8. So, 0 is between y of -1 and y of 3. So, y has a 0 between -1 and 3 by the intermediate value theorem. That's it. That's all there is to it. If you're just asked to show that something has a 0 between some point and another, it's a clue that you should use the intermediate value theorem, because all you need to know is to know that it's negative at one end and positive at the other end, and since it's a continuous since the function is continuous. Since it's a continuous function, I know that the intermediate value theorem tells me that it must pass through every number between -8 and +8, and 0 is one of those numbers. Okay? Awesome. Now this doesn't tell you how many zeros that function has, but being a quadratic, it ought to have 2. But now we know it has at least 1. Okay. That's the intermediate value theorem. Now, technically, you do use the intermediate value theorem while you are doing the bisection method for finding a 0 of a function, because the intermediate value theorem says that if you can find any 2 points, one's above 0 and one's below, then the 0, whatever the real 0 is, must be in between, and you can just keep making that interval smaller and smaller and smaller until you get it to the point that you want it to be at. Okay, that's the intermediate value theorem. To remind yourself where the intermediate value theorem belongs, the intermediate value theorem doesn't talk about derivatives at all. There is no mention of a derivative in the intermediate value theorem. So to distinguish it between the mean value theorem is about derivatives, and so is Rollies theorem. So this is the one that's not about derivatives. So I'm just going to make that point. IVT it's not about derivatives of f. It is a little dangerous to say that, because you can use the intermediate value theorem to show that something has a turning point by using the intermediate value theorem on its derivative. So, so remember that you are allowed to use f dashed in that spot. It's just that the other ones tell you about, knowing about the function tells you about its derivative, and vice versa. This one is just about a single function, and you're not looking at its derivative at the moment, you're just looking at one function. All right. The next theorem would be Rollies theorem. And I know it's supposed to be Rollies theorem, but too bad. I pronounced Euler for many years, and sometimes I still do. If I write it, no one can tell that I pronounce it wrongly. Okay, so Rollies theorem does concern the derivative of a function. Okay, and it's something like the intermediate value theorem. It tells you that there must be a place where the derivative is 0. So, if f of x is continuous on some closed interval, meaning it's continuous everywhere in between, and it does go all the way up to something at b and all the way up to something at a, and differentiable on open interval AB. Okay, technically you can't be differentiable at the edge of a zone, because to be differentiable the derivative has to exist on both sides, and if the function doesn't exist on the other side then there's no derivative there. So that's why they specify that it's the closed interval for being continuous and the open interval for being differentiable. So if it's continuous there and differentiable there, and if f of A equals f of B, then there is a C strictly between A and B with f dashed of C equals 0. note that here it talks about the function itself. The function is equal. Most of the time it's supposed to be equal to 0, but it doesn't matter. They just have to be equal to each other. Then there is a c somewhere between a and b with the derivative equals 0. So what we're doing is we're using information about the function itself to tell us something about the derivative of the function. So your Rollies theorem connects information about the function to information about its derivative. Okay. And the picture is so there's my A and there's my B, and the FA and FB are at the same height, and so therefore somewhere in the middle there's a C which makes this come out to 0. Okay, so because the slope is the tangent. So at this point we get f dashed of c equals 0 on that tangent line. There could be more than one. It could turn multiple times between A and B. That looks like a 0 there, sorry. It could turn multiple times between A and B, but we do know it has to turn at least once because it has to come back. It goes past A and then it has to come back down to get to this spot here. Okay? And it doesn't actually matter that they're equal to, that it doesn't have to be equal to 0, but that's the most useful version of it. Okay? So that's great, that's the actual Rollies theorem, but there is a better version of it. There's a better version which specifically talks about how many zeros a function has and how many zeros its derivative has. And you're allowed to use that version of Rollies theorem. So what it says, what it says is that if f of x has n zeros, then that means we know that f dash x has at least n minus 1 zeros. None of those n minus 1 that we just mentioned are equal to the n zeros that we had there. All of these n minus 1 different to the zeros of f. Okay? That's the most useful one. Yep?
Is it meant to be at most, not at least? Or?
No, at least. Definitely at least. And I'll explain why. Someone just asked, is it at most or is it least, for the purposes of the recording. I'll just explain why that's true. It goes like this. So f of x, this is the x-axis here, has zeros at maybe these places here. Rollies theorem says that there has to be a 0 of the derivative somewhere in here. Somewhere in there. There has to be one here, there has to be one here. Okay? But Rollies theorem doesn't say how many there are in between here and here, so there could actually be more. So there's f has 4 zeros, and f dashed has at least 3, but Rollies theorem doesn't guarantee that there's exactly one here. There could be like 15 in here and we wouldn't know. So that's why it's at least. And you also know that the place where the derivatives are 0 is definitely between the zeros of f. So you do know that all of the n minus 1 places where the derivative is 0 have to be different from all of the n places where y is 0. Okay, so this place where the derivative is 0 can't be equal to a or b because Rollies theorem says that it's strictly between those two endpoints. Okay, so that's one version. But also you can do it backwards. If the derivative has n zeros, and just to make it different to the other one, I'll use a different letter so that I don't get confused. If the derivative has m zeros, then that means that the original function has at most m plus 1 zeros. Okay? So this is backwards, right? So we've got one where we can know about... I'm going to attempt to draw a diagram of this. Maybe not. So if we know how many zeros a derivative has, then we can work backwards and say, well, the function can't have any more than that. And the picture is the same, but we're working backwards. We know that it has derivatives at these places. Derivative is 0 at these places. There's turning points there. So it could have 4 zeros here, but I couldn't have 5 because then Rollies Theorem would tell me that I get another 0 for the derivative. So I had 3 zeros here. I have at most 4 here, but I can't have a 5th one because that would guarantee yet another 0 of the derivative, and I only had 3 for the derivative, so it doesn't work. So we don't actually know how many zeros the f has at all. If we only know about the derivative's zeros, the function itself might have no zeros at all, but it can't have any more than m plus 1. Okay. So now let me do an example of using that. Show that f of x, which is equal to x plus tan x, has exactly 1 0. When we say 0, we mean x that makes f come out to 0. Okay. So, we need a theorem that tells me how many zeros that function can have. Now, the Intermediate Value Theorem tells me about what f can come out to. It says that if I can find a place where f comes out to less than 0 and another place where f comes out to more than 0, then there's definitely at least 1 0 between them. Yep?
Just with the Rollies theorem, say, I know you said before that they have to be, the derivative where it's equal to 0 has to be between the 2 points.
Yep.
Does that discard any chances of there being a turning point at like A, B, C, or D there?
Yep. So the question for the recording is, I've said here, all of these n minus 1 are different to the zeros of f, and you're saying, does that exclude the possibility, I know there's a 0 here and a 0 here and a 0 here, does it exclude the possibility of there being a 0 at one of these points? And the answer is no, it's perfectly possible for there to be zeros at those points too, but the n minus 1 zeros that I mentioned in Rollies Theorem are different to those ones, but there might be even more at those points as well. I mean, there might be even more in between these two. So it just guarantees that there's at least one that's different to A and B, and there's at least one that's different to B and C, and at least one that's different to C and D, but there could be any number of them in there, and there could also be ones equal to A, B, C, and D, and I will do an example that specifically uses that fact. Right. So there is a secret... It's not really a theorem, but there is a secret thing that you need to know. Yep?
Question. Is your function continuous?
That function? Between minus pi on 2 and pi on 2. Thank you. Yeah, I was asked, is my function continuous? And no, it has discontinuities at every pi from pi on 2. Okay. Now that would be great, right? Because I could sub in minus pi on 2 and pi on 2 into this function, but it's not defined at those places, so I can't use the intermediate value theorem at those spots, which was a problem. But there is this secret thing that you need to know, which is if you happen to think of a 0 just off the top of your head, then there is one, right? So note that f of 0 is 0 plus tan 0, which is 0. So it does have at least one 0 because I found one. So x equals 0 is a 0 of f. So if you, sometimes they will be expecting you to look at it and go, oh, I can guess one. It's always okay to guess one. So I have found a 0 and it's x equals 0. So I know that it has at least one, but now I need to make sure that it doesn't have any more. All right? Right. So I need a theorem that will tell me how many zeros it has, and Rollies Theorem tells you how many zeros something has. At least it narrows it down. So let's find the derivative. The derivative is 1 plus sec x all squared. Okay. And if I can find out about the zeros of the derivative, it will tell me about the zeros of the function. So, now I need to know how many zeros this has. I've got at least a couple of people shaking their heads. This doesn't have any zeros at all, because that's positive, and plus 1 means that this is always more than 1. It can't be 0. F dash x equals 0 has no solutions, right? So f dash has no zeros. All right, so now let's use this fact just up here. F dash x has 0 zeros, therefore by Rollies theorem, fx has at most 1 0, because that's 0 plus 1. Therefore, by Rollies theorem, f has at most 1 0. So it has at most 1, and we've found 1, so therefore it has exactly 1. Since there is a 0, it has exactly 1. Okay, so this uses two ideas. Usually if you're trying to find out how many zeros something has using Rollies theorem, you need Rollies theorem to either tell you it has at most a certain number, or it might tell you it has at least a certain number, and then you need some other bit of information to tell you how many it actually has. Okay, so I used this bit which told me it had at most 1, and then this bit I found 1, and so therefore it must have exactly 1 because it has 1. So this here, if I didn't know that it already had a 0, all that Rollies theorem would tell me is it had at most 1, and it might not have any at all. It could have 0 or it could have 1. But since I found 1, that rules out the 0, and now there's only 1. That's page 4. Okay, let me do another example of using Rollies theorem. How many zeros does that function have? Okay. Without finding them, right? Using Rollies theorem. Sorry, how many zeros does f dash x have if f of x equals that? Sorry, sometimes I have to be, as I said, I warned you. How many zeros does f dash x have if fx is that? Much better. Okay, so this question, you can tell it's Rollies theorem because Rollies theorem concerns the derivative and the function and how many zeros they have. Okay, so I can tell I have to use Rollies theorem to do that. And I'm going to have to use the version that I'm going to have to use the first version. I'm going to have to use this version. No, the other version, this one, which says, where'd it go? This version, which says if I know about the derivatives of the zeros of f, I can find the zeros of f dashed. Well, find out how many there are. So let's see, because I know about f. Okay, so I can at least start with f. Function f has zeros at 1, minus 2, and 5. Okay? That's exactly how many zeros it has. It has 3. So therefore, according to Rollies theorem, f dashed has at least 2. And it doesn't just have at least 2 zeros, it has at least 2 zeros, and those 2 zeros that we're thinking of are not equal to 1, minus 2, or 5. Has at least 2 zeros, and these two mentioned are not equal to 1, minus 2, or 5. Okay? That's what Rollies Theorem will tell us. So far we have a 0 between 1 and minus 2, or no, actually, not between 1 and minus 2. We have a 0 between minus 2 and 1, and a 0 between 1 and 5. You have to put them in the right order for Rollies Theorem to work. Okay? That's good. So, that's great. We know it has at least 2 zeros. Cool. Let's see. Function f is a degree 4 polynomial because it has 2 x's here and 1 x here and 1 x here. That would give me an x to the 4. So function f dashed is degree 3. Okay? And so therefore, f dashed has at most 3 zeros. So that's secret theorem, the second secret theorem, which goes a polynomial has at most as the number of zeros as its degree. We didn't use the Intermediate Value Theorem, we didn't use Rollies Theorem, we used another piece of information that we knew about functions already, which is if you have a degree 3 polynomial, you can't have any more than 3 zeros. In fact, a degree 3 polynomial has to have at least 1 zero, but we've already covered that. So what have we got? We've got at least 2, we've got at most 3. So my f dashed has either 2 zeros or 3 zeros, but I don't know which one it is yet. I'm supposed to narrow it down exactly to the right number. But I know it has either 2 or 3. Okay, well, I either have to rule out the possibility of there being any more zeros, or I have to find another 0. Now, what we mentioned before is that there's nothing in Rollies' theorem that precludes there being a 0 at 1 or minus 2 or 5. So maybe I should start looking there. And this is the quickest way to solve this problem. This was one of the tute questions, by the way. You're not supposed to actually find what f dashed x is in this question. They often explicitly say, find out how many it has without finding without finding it. Let's write fx as x minus 1 squared times g of x. So that g of x is all of this stuff here. Then f dash x, using the product rule, I'll differentiate this bit, which will give me 2x minus 1, and I'll keep the g of x. And then I'll keep that bit, and I'll differentiate the g of x. So I haven't actually quite found the formula for f dashed. I've avoided actually finding the real formula for it because I still haven't considered what gx is. But notice that both of these have an x minus 1, so therefore f dashed of 1 is 2 times 1 minus 1 times g of 1 plus 1 minus 1 squared times g dashed of 1, which is 0. So we found another 0, which is equal to 1. And the zeros that we already found, we knew were not equal to 1 or minus 2 or 5. So this is a third 0. Therefore, f dashed has exactly 3. Okay, so let me just draw on this so that you can see what I did. This is where I use Rollies Theorem to try and figure out how many zeros it could have based on the zeros of f. This is where I narrowed down that it couldn't be any more than 3 using the fact that it was a polynomial. And this was the bit where I guessed a 0, sort of. You know, I used some other information about how derivatives work to tell me that there was another 0. So those two that I just did are classic Rollies Theorem sort of questions. Like one where both of them involve you happening to think of a 0, okay, which is perfectly appropriate. The only other situation that might happen is that you might be able to say, well, using some information, I know there's another 0 between -4 and -5, which doesn't include any of the ones we've got so far. Okay. What page was that? 5. The last theorem is the mean value theorem. So do remember, we've seen 2 theorems, but we've also seen 2 other useful bits of information, which is a polynomial of degree n has at most n zeros, and also that if you happen to think of a 0, then there it is. The mean value theorem. Okay, well, the mean value theorem is, well, it doesn't look like Rollies theorem, but Rollies theorem is a special case of it. It's called the mean value theorem because of integrals. But when we write the mean value theorem, we write it in terms of derivatives. So I'll just explain how that works in just a second. But it goes like this. If f is continuous on AB and differentiable on AB, then there is a C between A and B with f dash C equals f of B minus f of A over B minus A. That's the mean value theorem. Now, way back in the dim dark ages of Maths 1A, someone defined for you the meaning of what we've said mean when we say the mean value of a function. So we can say the mean value of a function is its area divided by its width. And so what you do is that sort of says that, well, area would normally be height times width. And so if you find the area first and divide it by the width, that should give you the height. And this is actually called the mean value theorem because of integrals, because areas are integrals. And that's because this here is the integral of f dashed. So this is actually saying that the average area of f dashed, there is a function that there is a point at which you can get to the average area. But that's what it says in terms of the name mean value theorem, but we don't use it that way in Maths 1B. We use it like this. Now, do remember that when I draw these pictures, I always put the f of A below the f of B, but that's not strictly necessary. It could be the other way around. So no matter what your function does, we have the average slope, the mean slope, which is this. If you've ever let me borrow one of your a pacer pencil from you in the Maths Learning Centre, you will know that I will break it because I press too hard. That's the average slope. So that red line, the slope is f of B minus f of A, that's the height, over the B minus A, that's the width. Okay? And what it's saying is that there must be at least one point somewhere in between A and B where the true slope, like the tangent, has the same slope. Okay? So there must be at least one point somewhere in between. My maths lecturer, when I did Maths 1B, said that it's something along these lines. I quite like this example. So suppose this is the pub, and this is your house, and you're drunk. And so to get from the pub to your house, you walk along this sort of wiggly line. The mean value theorem says that at least some point between here and here, you were facing the right way. As long as you didn't bounce off any... So there is a caveat there. It has to be differentiable, so it's not allowed to have any kinks, so you're not allowed to bounce off any light poles along the way. So if you didn't do that, you can be pretty sure that at some point you were facing generally in the right direction, according to the mean value theorem. If that helps you remember it, awesome. Okay, so, just let me add in green here, the slope of this line is f dash c. Okay, so we have a tangent at C, which we don't know where it is, but we know there is one, and it has the same slope as the straight line which goes from this point to this point. That was Nick Bookdale. If you ever meet him, then you should bring that up. Okay, so that's the mean value theorem, and the mean value theorem is used in awful proofs. Okay, so now I need to find an example of a proof that uses it. Just give me a second. So, does someone have on hand a question that they think would be a proof involving the mean value theorem that they would like me to do from an exam, maybe? No? Maybe? Because I'd probably like to do one that's, in your head. I have found one, so you can keep looking, but I've found one that was in the lecture. Did you find one?
Yes.
Can I have a look? I've got another one too. Okay, let's start with this one. Okay, so what I did, this is all great using the mean value theorem, but please, there's two parts to what I want you to get out of this. One is proving stuff using the mean value theorem, and the other one is proving stuff. Okay, so proving is a really general skill, and it's not a particularly well-defined skill, but it is still a skill, and anything you learn proving anything should be useful to help you prove other stuff too. So I'm going to do an example here. This is from semester 1, 2011. So that's what it is. Semester 1, 2011 exam, calculus question 5B. Okay. See, look, the first part A is state the mean value theorem. So you just need to know how to say it. Right? It's a mantra. You can say it to yourself before you go to bed. Like with the times table, stick it on the back of the toilet door. Or, if you're a man, above the toilet. Or both, just in case. So, use the... Now that'd be a great app, something that you could put stuff to remember on your phone, so that just had, you can put it as photos, so that when your phone's doing this little photo thing on the front, you could see your math stuff. Really cool. Or in your iPad, it just scrolls through photos of math stuff you're supposed to remember. Sorry, I've just been to a thing about, they're all into using technology for education, or at least they're trying to get everyone to be into it. And they're never really useful. I like that particular one. So, using the mean value theorem. So it says here, you can't read it from there, but I'll read it aloud for you. Use the mean value theorem to prove that if G is a... Why will it not zoom in? That doesn't have a zoom button on it. Ooh. Use the mean value theorem to prove that if g is a continuous function defined on the closed interval ab such that g dashed x is 0 for all x in ab, then g of x is a constant on ab. Okay. So the first part to proving anything is to know what the beginning is and what the end is. Okay, so we need to know what information was given to begin with that we can just assume is true, and what is the final endpoint that we're aiming for. This is the end. Gx is constant on AB. That's my goal. So if you've ever been in the Maths Learning Centre and been observant, you would notice there's a big thing on the wall about solving problems, and one of the questions for choosing what to do is what's the goal? And then we've got this information that we've started with. We've got that g is continuous, it's defined on the closed interval, and the derivative is 0 for everything in AB. That's the information we've got to start with. Okay, so now we need to understand what everything means. So continuous on AB, cool, we've got that. The derivative is 0, pretty cool what that means. But note that saying that the derivative is equal to 0 says that the derivative is defined. So it's differentiable. Okay, because we're able to find the derivative and the answer is 0. So we have a function that's continuous on AB, closed interval AB, and differentiable on the open interval AB. So obviously we're allowed to use the mean value theorem because that's what the mean value theorem starts with. Okay. All right. So what I'm going to do is, this is how I do a proof, is I put the stuff I started with at the top and the stuff I want at the bottom and hope that I can get from one to the other. It's a great strategy. So, we have that g is continuous on AB, g dashed on AB. Okay. Right. So we're supposed to say, down the bottom somewhere, therefore, yeah, maybe a bit higher, therefore, g of x is constant on AB. Right? So we're supposed to fill in stuff in here, and then the proof will be done. So if you never get to that in your exam, you could say, insert working here. At least you've shown that you know what you understand the question. Okay, so g of x is constant on AB. Well, let's think about what that means. What does it mean for a function to be constant? That means you'd have to say that g of x equals k for some k. I don't know what the k is yet, but that would be right. That's what I'm aiming for. So I might have to just leave a gap. So therefore g of equals, and I need to put something in that spot. I'm not sure what it is yet. For all x in AB. If I could show that no matter which x I picked, it always came out to the same answer, that's what it means to be constant. So I'd normally pick a k. I normally put k there if I was thinking about it just generally, but this is the end of my proof. So presumably by the time I get to the end of my proof, I'll know what that number is, at least in terms of f of a and g of b and that sort of thing. All right. Well, they've told me I have to use the mean value theorem, so they give me a hint. But even if they hadn't told me that, I've got a clue because I've got the beginning of the mean value theorem here. I've got that it's continuous and differentiable. So it's either going to be the mean value theorem or Rollies theorem because they're the ones that start like that. Okay, so well, the mean value theorem says, by the mean value theorem, there is a C between A and B with G dash C equals G of B minus G of A over B minus A. Yep? All right, well, I do know that G dash C is 0, right? Because I've been told that G of that's always 0. Okay, well I'm going to give this a go. I might have to fix my proof in a second. Alright, so we've got that, therefore g of b minus g of a over b minus a is 0, so g of b minus g of a equals 0 because we can times by the b minus a, so g of b equals g of a. Cool, so I know that g of b is equal to g of a, but I really want to show that everything in between a and b is equal to g of a. Crap. That's okay. I reckon we can fix it, because this argument ought to work even if I didn't choose a and b. If I had chosen like a and any other number at all, it should have worked still anyway. So how about I go, of course. Look, I'm supposed to show that this is true for all x in a and b. And when I do subspaces and I'm supposed to do something for every, I start with a let. So I should say something like, let x be between a and b. Yep? So, by the mean value theorem, there's something between a and x that works as well. So instead of using the mean value theorem on this entire interval, I'm just going to use it on the bit between a and x, whichever x I'm up to at the moment. Okay, so that's the mean value theorem between a and x. And then I get this. Yep. And then I get this. And then I get this. So g of x is equal to g of a for every x. So this number here is g of a. All right. Just to be sure, let's say consider the interval ax. Right. So let's just read that forwards. G is continuous on AB, G dash is 0 on AB. Let x be a number in AB. Consider the interval from a to x. By the mean value theorem, there is a c between a and x, with g dash c is equal to gx minus g of a over x minus a. Therefore, this is equal to 0. Therefore, that's equal to 0. Therefore, that's equal to g of a. So therefore, g of x is equal to g of a for all possible x's between a and b. Therefore, g of x is constant on ab. That's my proof. So, what lessons could I learn from this proof about how to do proofs?
Write it in pencil.
Write it in pencil. That's a great lesson. That's a good lesson. If you're doing a proper assignment, you'd write it again, right? But yeah. And write it in pencil, which basically means that proofs don't always come out right the first time. And the other one is that proofs are not always written on the page in the order they're read, because I wrote this much later. So maybe leave some gaps between things just in case you want to fill things in. Okay? I hope I wasn't just acting. Sometimes I am, but I wasn't just acting. I didn't know how to prove that already. So I just had to make it up. Sometimes I do know how to do it already and I am acting, pretending that I don't know how, but I really wasn't today. Of course, I could be acting saying that too.
With that, if you'd stated that, if you've done it the way before with A and B, and you'd stated that G of A equals G of B, can you, if you've written your whole proof, can you just say since G dash of X is 0 for the whole thing, like it's continuous between them, there has to be a straight line?
So the question for the recording is, before we had it with G of B equals G of A, could you just sort of fiddled at the end to convince people that that meant that it had to be the same all the way between B and A? No, you couldn't. Because we've only made a statement about G of B and G of A. We only have made a statement about what happens at the two ends, and we have no guarantee. So all we've proved in the first one, in terms of pictures, is that G of B and G of A are the same, but we have no clue what's happening in the middle. So what we've actually done is we've picked an x and we've actually proved that this is the same as that for every possible x all the way along. Yeah. So, however, if you had got that far and you just didn't know what to do, you could say, I understand that this doesn't prove that it's the same for the whole thing across, but I'm not sure what to do. And at least you would have shown that you know how to begin the proof. Yep.
If you know G of A equals G of B and the slope is 0 between that whole gap, then can you explain that as a straight line?
So someone said if you know that G of A equals G of B and you know that the slope is 0 the whole way along, can you just say, nah? So the whole point is that the only reason that we know that that's true is because of the mean value theorem. So all of those things that our instincts tell us must be true, for a mathematician, instinct is great, but things aren't true until they're proven. Well, then, you know, we don't know they're true until they're proven. Presumably they're always true, regardless of whether we prove them or not. But, yeah. And yes, that's just not how it works. So that would be like fudging it. And you'd be using a lot of other information about how functions work generally, and you just couldn't be sure that there was just some particularly crazy function that was like defined on the irrationals here and the rationals here that just didn't work that way. And so just because you can't think of one doesn't mean that there isn't one, which is the problem with maths, really. Okay. So there was another example of a proof. Do you want me to do that one, like in another exam? Did you want me to do that one too? Was that a different one?
Yes.
Sorry? Oh, we're supposed to prove the mean value theorem. What? Actually, yes, they would be, but they didn't ask us to prove that. Sorry, someone just, while I was talking, someone just said at the end there, I said g of x is constant on the interval AB. Is it supposed to be square brackets AB? Well, yes, we've actually proved that it's equal to g of A also at A and at B, but they didn't ask us to prove that, so I didn't end with that. Right, so this is, I'm just about to do semester 1, 2012, calculus question 4. Okay. Okay, so they were really nice in 2012. They told you the mean value theorem. You didn't have to remember it yourself in 2012. No clue what your lecturer thinks about it. So they've told you the mean value theorem there, and then they've said, what is the equation of the straight line that connects those 2 points? Denote that line by y of x. I should actually just tell you what that equation is, because most people know how to do it, but there's a really kind of quick way of figuring it out. So in case you don't know it, I just thought I'd show you. So this is part A. So the line from A, f of A, to B, f of B, just as a quick picture, we've got that line. Okay. Most people would go, well, it's y equals mx plus c for some x and some c, and then you figure it out. You don't technically need that. What you do is you imagine a point x, y on this line, and you go, well, the slope from here to here is the same as the slope from here to here. And so you go y minus f of a over x minus a is f of b minus f of a over b minus a. That's the slope from here to here. That's the slope from here to here. And that's the equation of your line. but you probably want to rewrite it like this. So you put that up there. So that goes up there, and then the f of a can come over. And that's the equation of the line that joins those 2 points. It's the quickest way, and it is the way that they wanted because it's the one that will work best in the mean value theorem. Because notice that if you put b in this spot here, then they neatly cancel each other out. So if you put b in for x, you'll get the b minus a and the b minus a will cancel each other out, and then you'll get f of b minus f of a plus f of a, so it'll come out to f of b, exactly as it's supposed to. And of course, if you put a in that spot, a minus a is 0, and you just get f of a. So that's the quickest way to find the equation of the line between 2 points if someone ever asks again. Okay, part B says, prove the mean value theorem by applying Rollies Theorem to the function g of x equals f of x minus y of x, where y of x is the equation of the straight line in part A. Right. So, they've told us that we've got g of x equals f of x minus y of x. So that's g of x minus the equation of the line. And we're supposed to apply Rollies Theorem to it. Okay. Well, Rollies Theorem says that if I can show that f of, well, in this case g of a equals g of b, then Rollies Theorem says that g dashed will be equal to 0 somewhere in between. Right. So what I actually want to show at the end is somewhere down here, my final statement is I want to say, therefore there is a c with f dash c equals f of b minus f of a over b minus a. That's my goal, right? That's the mean value theorem. So my aim is to prove the mean value theorem, so my aim is to prove that statement because that's the end of the mean value theorem. So somewhere along the line I have to find the c, or at least show that it exists. So let's see. Well, in Rollies Theorem I need to know what the function is at the two ends of the interval, so I should find that. So g of a is f of a minus f of b minus f of a over b minus a minus a minus f of a, and that's 0 just there, so that cancels out, and f of a minus f of a is 0. And g of b would be f of b so what I've done is I've subbed in this one I put in a everywhere there's an x in this formula. This one I put in b everywhere there's an x in that formula. Now the ba and that will cancel each other out. I'll have f of b minus f of b, which is 0, and minus f of a, which is plus f of a, minus f of a, which is 0. Okay, so therefore, by Rollies Theorem, there is a c between a and b with g dashed c equals 0. So all I need to do is figure out what g dashed of c is. So I might run out of room here, I'm sorry. So, yeah, okay. G dashed c, well, g dashed x, let's see. Well, I differentiate that would be f dashed x. The derivative of the f of a would be 0. And this is just a number, so that will stay there when I do the derivative. And the derivative of, because it's a number multiplied on, it will stay there. And the derivative of x minus a is 1. Sorry, I need more space. I'll write that again at the end. So we have that g dashed c is f dashed c minus f of b minus f of a over b minus a, which is 0. So therefore f dash c equals f of b minus f of a over b minus a. Magic. And that's exactly what we wanted to show. That's the mean value theorem. So that's a really bad there, sorry. So there is a c with f dashed c equals f of b minus f of a over b minus a. Okay, so the key is I knew what I was headed for, and the real key to this proof was having the equation of your line neat. So when the person who wrote this exam, they went, oh, that's really easy. But it's only really easy if you wrote the equation of your line in the right way. So for future reference, always do your equations of your lines in that way. At least if you're trying to do stuff with the mean value theorem. But it's a really useful way of finding equations of lines, and it does the trick. All right, that's probably plenty, unless on the mean value theorem, unless unless someone wants anything else before I move on to series, which is the other thing people ask me about. No? You're all feeling awesome? Excellent. No. Cool. What I might actually do is just stop the recording